All right, everyone. Hello. So now we're going to get into one of my favorite topics here in calculus, which is related rates. Now, we've been getting some good practice taking derivatives of functions, either explicitly or implicitly, but for the most part, many of these functions were devoid of any context essentially in a real life scenario. So yes, we were taking product rule, quotient rule, chain rule, using implicit differentiation, but again, they were just mostly exercises in a book. But now this is all going to change because, well, we've said that calculus is the mathematics of change. So let's see how, and we know that, well, life is very chaotic. So let's see how we can apply calculus to other real life scenarios. Now I want to begin here with a simple example. Let's say that we have a spherical snowball that melts in such a way that at the instance at which its radius is 20 centimeters, its radius is decreasing at 3 centimeters per minute. Now, at what rate is the volume of the snowball changing at that particular instant when the radius is 20 centimeters? Now, this one here certainly looks like a problem that it's different from the problems we encounter in pre-calculus because now we are dealing here with rates. Now we can see that in this problem we have two quantities that are changing. The radius is decreasing at a function of time because we can see that, hey, it is decreasing at 3 centimeters per minute, which in turn leads to a decrease in volume, right? Because, well, if you decrease the volume of the radius of a sphere, then you would also be decreasing its volume. Now, notice here that both functions are functions of time. In this case, they're both decreasing as time progresses. So we will be needing derivatives with respect to time. Now, before we solve this problem, I want to have a little bit of a warm-up here with implicit differentiation. So let's take a look at this problem here. Problem number 1 asks us to find the derivative with respect to time of y of t cubed. So when working with these problems, we can see here that, okay, it looks like y is a function of time, or t, and it is being cubed, so we can see here that we need a chain rule. So the derivative here would then be, well, we bring down the 3, y of t squared times, very important here, guys, remember it's the derivative of the inside, so it is going to be the derivative of y with respect to t. Okay, so hopefully by now we feel more comfortable with implicit differentiation. So this problem here, I'll let you guys try it and send me the picture on Friday. It's not too bad. Okay, now let's take a look at other type of problems. Now, because most of the problems that we're going to be dealing with when we're doing related rates, they're going to be functions of time. Then for this couple of examples, let's assume that they are also functions of time. So I'm just going to have here say that if we have x of t, rather than writing x of t all the time, I'm just going to say that x of t is the same thing as x and y of t is the same thing as y. Okay, so let's take a look at another problem here. Let's say that we're given x squared plus 5y equals to 10, and we want to find dx dt when y is equals to 3 and dy is equals to negative 1. Okay, so again, remember here, guys, x and y are functions of time. Now, when we were doing implicit differentiation before, well, normally we just assume that y was a function of x, so it had its derivative. Now in this case, because we're treating both x and y as functions of time, when we take the derivative with respect to time of both sides, well, we are going to end up with a dx dt and a dy dt. So let's see here. So we have the derivative of x squared plus 5y equals 2. Take the derivative of the right hand side as well, 10. Okay, so let's see. And this is what I was talking about. Right now, when we find out what is the derivative of x squared, then it's going to be, I'll put it here, we need chain rule, don't forget. So the derivative of x with respect to t, not x, is going to be 2x times the derivative of the inside, which would be dx dt. Did you guys see why? Because basically this is just x of t. Okay? Now on to the next term, plus, so what is the derivative of 5y? Well, that one here is going to be 5 times dy dt. And that is equals to the derivative of 10 with respect to time, or t. Well, that's just 0. Okay, so we want to solve for dx dt. So we would have here 2x dx dt is equals to a negative 5 dy dt. Now at this point, if you guys want to plug in whatever the values that we have here, we don't know what x is, but we have here that y is 3 and dy dt is negative 1. So I'm just going to plug them in here. So we have 2x times dx dt is equals to a negative 5 times a negative 1. And actually over here, guys, there was a typo. Didn't catch it. X was equals to 3. So we have here 2 times 3 times dx dt, which gives us here 6 dx dt equals to a 5. So dx dt is equals to a 5/6. Okay. And again, well, this was just basically a problem with implicit differentiation. Okay. Now on to this next example. Now for this one here, I'm gonna let you guys try it here. Well, yeah, I'll let you guys try it. So this one here, let's make it due Friday. And the solution here, guys, is a negative 1. So you guys would know if you're doing the right thing. Okay? And again, remember, the key here is we're taking the derivative with respect to time for x, which is a function of time, and y, which is a function of time. So we need the chain rule. Okay? Okay, guys. So now that we've reviewed a little bit of implicit differentiation here, let's go back to the problem. Now, this problem here, it is a related rates problem because as we have seen, the radius is changing, so there's a rate of change there. And as the radius changes, the volume also changes. So you see here, those two rates, they are related. So let's see, how do we approach this type of problems? Well, the first thing that you want to do, typically in an example like this, is to create a diagram to give you guys a better sense of understanding of what is happening in the problem. So if we make a diagram here, I'm going to be drawing my snowball. Boom. Perfect circle. Maybe not perfect. So let's see here. Okay, so here's our snowball. And what do we know about the snowball? So it is melting. So here we go. It is melting. It's creating a little bit of a puddle here. And it's melting in such a way that at the instant in which its radius is 20 centimeters, so let's draw its radius here. Okay, and right about here. So let's say that its radius is 20 centimeters. It is decreasing at a rate of 3 centimeters per minute. So what we have here is that the radius, it is decreasing and the rate at which it's decreasing, it's 3 centimeters per minute. So okay, so when we were talking about rates of change, well, how do we write a change in the language of calculus here? Well, we see here that the radius is changing as time changes, and it is happening at negative 3 centimeters per minute. So why is it negative? Well, because it was decreasing, so it's a negative change here. Okay, so here's a diagram. Now, what else do we do? Well, we want to identify the rates in this problem, what we know and what we don't know. So from above here, we saw that, okay, the rate at which the radius was changing was negative 3 centimeters per minute. Okay, so what else was this problem saying? Well, it wanted us to find out at what rate is the volume of the snowball changing when essentially the radius is 20 centimeters. So now they are talking about the rate of the volume. How much is it changing by? So what is the rate of the changing volume as time goes on? Okay, so those are our two rates. Okay, so there's no other rates going on. But over here, no, let's go on to the next part. Okay, now the next part, which is very, very important, one of the most important steps here, is we want to come up with an equation that relates the rates. So what is the equation that, in this case, relates the volume and the radius? Let's see here. Sorry about that, guys. I blanked out on how to spell radius for some reason. So what is the equation that relates the volume and the radius? Okay, so in the case of a sphere, maybe some of you guys might remember, maybe yes, maybe no, that the volume of a sphere is given by the equation 4/3 pi r cubed. Okay, so you see here now I have an equation that is relating the volume and the radius. Now really in this problem, because both the volume and the radius are functions of time, then for this example I'm just going to illustrate it here by saying we essentially have volume as a function of time is equals to 4/3 pi, then the radius as a function of time that is being cubed. Now the reason I'm writing it like this here is that we see that they're both changing with respect to time, so we can find their derivatives. Okay, now once you come up with the equation, we want to differentiate, and we differentiate with respect to time here. In other words, we want to find, well, what is d dt of the volume. Now, okay, let's see here. So with our equations, we had the volume as a function of time here was equals to 4/3 pi r cubed, and we want to find out what is the derivative with respect to time. Okay, Now, if we're taking the derivative with respect to time, once again, notice here, guys, just like the examples that we were doing above, we will be needing a chain rule. So this one here, let's see, this 4/3 pi, it's a constant. So I'm just going to keep it out and ask myself, okay, what is the derivative with respect to time of r of t cubed? So using the chain rule here, we end up with 4/3 pi times, so the 3 comes down, so it's a 3 times r of t squared, and is that it? Nope, we still need to find out, okay, what was the derivative of the inside? Well, that the derivative of the inside is dr dt. Okay, so now I'm just going to drop the function notation there, and I'm just going to say, okay, then what we have here is dv dt is equals to, well, it looks like the 3's cancel, and we have 4 pi r squared times dr dt. Okay, so notice what you found here is an equation relating the two rates, the dv dt and the dr dt. Now, at this very last stage, now is when we want to substitute the values that we know. So in the problem, because we were focusing at the instant when r was equals to 20 centimeters. So at that particular moment, if you took a picture as the snowball was melting when the radius was 20, and if that picture for some technology was able to tell you the rate of change was telling you that dr dt was equals to a -3 centimeters per minute. So we can find out what is the change of volume then. So putting everything into the formula, we would get dv dt is equals to 4 pi. Now, one hint that I'm going to give you guys right now is that some of these problems can get a little bit tricky, I'm not going to lie. And sometimes if you're unsure of your answer or you're maybe a little bit lost, well, one way that we can determine whether or not we are essentially within the ballpark is to consider the units. So dv dt, so it's a changing volume over changing time. So what are the units that we could expect? Well, if we knew that the radius was changing as centimeters per minute, then the volume is probably going to be changing at a rate of centimeters cubed per minute. So if your final answer gives you the correct units, then you at least know that maybe you're not 100% right, but at least you're somewhat right. So let's see here. And I'm going to show you guys that, so how you can determine with the units. So if the radius was 20 centimeters, so the formula that we got here was dv was 4 pi r squared. So if the radius was centimeters, okay, so it's 20 centimeters squared times r dr dt, which was a -3 centimeters per minute. Okay, so as we can see here, if we simplify things out here, we have 4 pi times 20 centimeters squared. We get 4 pi times 400 centimeters squared times a -3 centimeters per minute. So we end up with 4 times 400, that's 1600 times -3, that's a negative 4800 pi. And what are our units? Well, centimeters squared times centimeters, that's centimeters cubed per minute. So you see here, okay, the units match. Excellent. So it seems like at the instant when R was equals to 20 centimeters, the volume was changing at a rate of negative 4800th pi centimeters cubed per minute. Now this last part you don't really want to write it in the problem, or you don't need to write it in the problem, but I wrote it down here to emphasize that we are only looking at particular instance. Okay? Now, on that note here, I want to give you guys a warning. Now, a very common mistake to make is to substitute the given numerical information, the quantities that we have here, way too early, essentially at the beginning of the problem. You only substitute after you do the differentiation. Because going back to the problem above, what happens if we went ahead and got our formula, which was, oh, we know that the volume was related to the radius by the formula 4/3 pi r cubed. Now, if we said that, oh, but r is 20 centimeters, then if you plugged it in, you get 4/3 pi times 20 cubed. Well, this is telling you the volume at the moment or the instant when R is 20. But this is telling you the volume, not how the volume is changing. So you got to be really, really careful with that, because in these problems, we're interested in how things are changing. If you plug in things directly, then you're not getting anything that's changing. You're just getting a value, okay? So really, really important warning here, because it's a really, really common mistake. I mean, I see it all the time. So you got to be careful. Now, some of the common formulas that we will encounter in related rates problems are, well, the areas of squares, triangles, circles, rectangles, volume or surface areas of cylinders, which I provided the formula here. The volume for a cylinder is pi r squared times h, which is essentially the base of a cylinder, which is a circle, with an area pi r squared times the height, which is just h, and the surface area here, which is 2 pi r squared plus pi r h. Now, other common formulas are the volume and surface area for sphere. So the volume of a sphere, as we saw above, was 4/3 pi r cubed, and the surface area was 4 pi r squared. Now the volume of a box, which is length times width times height. The Pythagorean theorem, very common, because we can use it to relate the sides of a triangle. Also trigonometric functions and the ratio and trigonometric ratios to get angles. So basically sine theta, remember that sine theta was essentially y over the hypotenuse, or y over r, dot, dot, dot. So all those trig functions, we're going to be using them. And also something that is not very common, so I'm going to go over one problem here, is the ratio of similar triangles. Okay, now for the rest of our essentially our video lecture here, I'm going to be focusing on problems, so you guys can see basically a more variety of problems involving related rates, because the steps that I do want you guys to follow, sometimes they're more like a guideline, but they don't necessarily work in a particular order all the time. So yeah, with that said here, let's take a look at a couple of problems.